Vector functions. We're going to talk about vector functions and space curves. So we have to be able to work in three-dimensional space. Planes fly in three-dimensional space. So, for instance, as engineers and scientists, we need to work in three-dimensional space. Section 10.1 orients you a little bit about how this works. So remember that you learned about vectors, right? You learned about vectors in chapter 9, and vectors had in three-dimensional space, a vector has an x, y, and z component. Well, for I want to say this the right way, for a vector valued function, okay, r of t, the components of r and t, the x, y, and z components, are all functions of t. And as t varies, the functions f, g, and h give different coordinates. And the different coordinates trace out a curve in space. Okay, so like a nice picture here that they have is here in figure 1. Figure 1 says this curve C is traced out by the tip of a moving position vector r of t. So for every value of t, r of t is a specific vector. And as t varies, the vector moves in space, like a pencil moving along a paper. As the pencil moves, the tip of that pencil traces out a curve in space. And and we call r of t a position vector. One moment here. So let's see, Mario says, in the examples we see the dimensions of the component vectors are the dimensions of the output are the same. Yeah, so the component functions give the coordinates of the position vector. That's right, that's right. So very good, very good. Well, of course, we can talk about then things like the domain of a vector function. Okay, so like for instance, in example one, let's say you have your position vector. Okay, r of t equals has components t cubed log of 3 minus t and the square root of t. Well, there then are your component functions f, g, and h, and we want to find the domain of this vector function. Well, you have restrictions there by the component functions g and h. So the log of the argument, right, the argument 3 minus t has to be greater than 0. Okay, so that means then that t would be, if 3 minus t is greater than 0, right, that's this requirement here. If 3 minus t is greater than 0, that means t is less than 3. But t less than 3, well, you also have that component function h of t, which is the square root of t. Well, there t has to be greater than or equal to 0. So that adds a second constraint on t. And therefore, hold on, I want to highlight it. Therefore, the domain of this position vector r is 0, including 0, to 3. And it's open at 3. So the domain includes t, it's from 0 to 3. It includes t equals 0, but doesn't include t equals 3. Okay, so that's the domain of a vector function. Are there any questions on that? All right. Of course, you can define the limit of a vector function. The limit of a vector function, and if you know, hey, if we're talking about here limits of a vector function, what do you think is going to be coming up with vector functions? If we're talking about limits of a vector function,
derivatives and integrals.
Derivatives. That's right. Good, Hunu. Good, Mario. We can take derivatives of vector functions as well. All right. So, okay. Well, let's look at an example here. Okay. We'll look at some of our own, but example 3 says describe the curve. Sorry, I want to get it. Describe the curve defined by this vector function, r of t. Okay, so there's r of t equals 1 plus t, 2 plus 5t, and negative 1 plus 6t. What do those parametric equations look like? They're parametric equations of what space curve that you've already seen. That's good. Good, Hunu. Good, Marwan. A line in space. Absolutely. Absolutely. A line in space. And sure enough, I'll highlight it all here. Sure enough, the parametric equations are parametric equations of a line passing through the point 1, 2, negative 1, and parallel to the vector 1, 5, 6. Okay, so that's fine. That's fine. And you know, they're using component notation, but you can also write plane curves in space in terms of vector notation. So there's an example of vector notation. Sometimes one is easier than the other. Okay, now what they have here, what they have in example 4, is they want you to sketch. Let me remove that highlight. They want you to sketch this helix. Okay, they want you to sketch this helix. Now, you don't know it's a helix, right? But what special things in our bodies consist of helices? What special things? Good, DNA. Okay, your DNA consists of helices. And so that's an example of the space curve, right? Well, let's see what the parametric equations are. Spines, well, you know, Mario, I'm not an expert on that, but, you know, okay. So, well, all right, well, x, y, and z equal cosine, sine, and t. And, you know, we know that x squared plus y squared would equal cosine squared plus sine squared. That equals 1. So whatever this space curve looks like, it has to lie on the cylinder x squared plus y squared equals 1. I mean, you know, that's true. It has to. X squared plus y squared equals 1 for any value of t by virtue of that Pythagorean trig identity. So you know, the curve has to lie on that cylinder. And given that, the x squared plus y squared equals 1 is a vertical cylinder. All right. Now, so the only thing we haven't talked about is z. Z equals T. Well, as T changes, that's going to cause this space curve to move up and down. So the X and Y component functions cause the circular behavior, and the Z component causes the vertical behavior. And so that's going to generate a helix. Okay, that's going to generate a helix. At T equals 0, you start out at the point 1, 0, 0. And there's your helix, the red helix. What's the value of T at that point 0, 1 pi over 2 in the picture? So as the helix takes on, as the space curve, the position vector of the helix takes on different T values, the position vector, which is like a pencil emanating from the, reaching out from the origin, tracing out the space curve in space, T equals pi over 2. That's right. Good Hunu would be that point there for 0, 1 pi over 2. Now, you know, we can graph that space curve using MATLAB. We can graph it using MATLAB. And I'll just point this out here. If we go to, let me go to application here. So let me go to the course content. There's course content. And click on the here link to see the, actually no, oh well, I'm sorry. I haven't created the course content for chapter 10 yet, but that's okay. We can still access the program. All we do is we go to MATLAB programs here on the left and click on that link. Click here, and there will be in section 10.1, there's a MATLAB program that will help you draw the space curve. Okay, so if you click on that link, it will bring up a file that I share with you, and you can download that file and then open it up in MATLAB. So if we do that, let me open up MATLAB here. Okay, and I'd like you to open up the MATLAB program too. Okay, this is the program right here. Okay, and I'm using called EasyPlot3. EasyPlot3, it allows you to do a plot quickly in three-dimensional space. That's why it's EasyPlot3. The component functions are cosine of t, sine of t, and t. And I'm going to say graph this, this space curve from 0 to 4 pi with a skip factor of pi. It's kind of a lot, kind of a big skip factor, but it works in this case. So what I do is I copy the code and I paste it on the command line. I go paste and then enter. Okay, and by the way, it's usually good to use the command clear vars, clear your variables. Okay, I'll copy and paste the code again, and I don't want, just so nothing interferes with the program, old stored variables. When you copy and paste, you should get a figure. Okay, so who if you're doing it with me, which I hope you are, who is getting a helical figure, getting a helix? Okay, let me see here. Good, and for some reason my figure, okay, wait, let me move this over. Hold on, there were some chat comments here. No, Mario, I like to do it this way. I'm not sure even how to post the code in chat. Mario's saying, can I post the code in chat? Well, hold on, let me try. It's good to try new things, right? Good to try new things. So I'm taking the code, and let's see, I'm going to try to paste it here in the chat line. Oh, okay, is that what you're talking about, Mario? Okay, very good. All right, I learned something new there. Okay, great. So, yeah, well, Charles, you make a good point. This helix doesn't look exactly like the helix in the book, because look at the axes. The x-axis and the y-axis and the z-axis are like the right orientation, but you're going the wrong way, right? The x is going like from going forward, it's negative. Going backward, it's positive. And the same with the y. Now the z's okay. Good, excellent, Marwan, excellent. So there's a thing you can do with the figure. There's a thing called, you go to Tools, and there's a thing called Rotate 3D. Rotate 3D. Okay, you can rotate the figure. Okay, yeah. Now it takes a little bit of effort, but you can get it where the x, y, and z axis are like what you see in the textbook. And I don't want to spend a whole lot of time doing it. Hey, there we go. We got it. There we go. How about that, huh? Is Dr. Duty skilled or what? I kind of don't know how I did that. I think I just kind of moved the cursor up or something, but I'm gonna kind of remember what I did. Oh, X is still reversed. No, X is okay, isn't it? Yeah, X is all right. Charles, do you agree? I mean, I'm seeing X on what you're saying. I have X being correct and Y being correct. Yeah, X should go like on the left, X should be like go from 1 to -1 on the x-axis. That's right. And the y-axis going from right to left should go from 1 to -1. And the z-axis should go from 0 to 15. But at least that's what I'm seeing, class. I apologize if you're not seeing that, but that's at least what I'm seeing. Who is seeing that on the figure that you're seeing? It should be that. At any rate, if you do the rotating, you can get the axes to be consistent with what you see in the textbook. Okay? Okay. So, yeah, so I'll let you kind of work on that, everybody. And let me go forward here now. Let me go forward. So another thing that I want to mention in the ebook here is lots of cool stuff. Example 6. They want you to find a vector function that represents the curve of intersection of a cylinder, of that vertical cylinder x squared plus y squared equals 1, and the plane y plus z equals 2. Okay, so in this example 6, here's a picture of in figure 5 of what they're talking about. And again, you could graph these surfaces on the in MATLAB, you have to use what's called the hold on command. If you want to graph two surfaces, well, I got to be a little careful. It's not, graphing a cylinder is not as straightforward as you would think. But let's just focus on this picture here. So figure 5, they drew that vertical cylinder and they drew the plane y plus z equals 2. And you can imagine that a plane is going to intersect the cylinder and the intersection will be a space curve in figure 6. Okay, so the plane intersects the cylinder in this space curve. And they've plotted some points on the space curve too. But what we want is we want to know the parametric equations of that space curve. So let me ask you, the space curve lies on what? What does the space curve lie on? It's part of it. Well, the space is the intersection. That space curve is the intersection. And hold on here. Let me just, maybe I'll bring this up a little bit. Hold on. And get this up a little bit. Okay, so you see you got a plane intersecting a cylinder. It creates a space curve. Does the space curve actually lies on both the plane and the cylinder? But if you had to describe the x coordinates and y coordinates for all the coordinates on that red space curve, look, they have some coordinates there that they have. What's true about x squared and y squared for each of those coordinates on the space curve? Is there some relationship? So like, okay, so the xy coordinates for the 1 point are 0, 1 for the bottom point. The xy coordinates for the next point are -1, 0. Third point, 0, -1. Fourth point, 1, 0. What equation do all the xy, good, that's what I'm looking for, Ellie. X squared plus y squared equals 1. And that's because x equals, so for like in terms of like horizontal movement, I mean the space curve looks like an ellipse, right, in three-dimensional space. But in terms of like horizontal activity, horizontal movement, x equals something and y equals something. What would the parametric equations be? If x squared plus y squared all equals 1, then we could let x equals something and y equals something. Here's what I'm trying to say. Let me say it another way. We know that x squared, well, hold that thought. X squared plus y squared equals 1, always. I want x to be a function of t and y to be a function of t. And I need functions of t that are gonna satisfy this restriction. Good. So, good, Ellie. X would equal cosine of t, y would equal sine of t. That'll work because cosine of t squared plus sine of t squared equals 1. So x would equal cosine of t y would equal sine of t. And now all I have to do is get z. I got to find out what z is. Well, remember, another requirement in this example 6 is that y plus z equals 2. That's another requirement. All the points on my space curve C satisfy, all the coordinates on the space curve C satisfy these two equations. So, gee, how am I going to get z? How am I going to get z? If y plus z equals 2, then what's z going to equal? That's right, Yunus. 2 minus y. That's right, Emma. So then z has to equal 2 minus what? 2 minus... So x is a function of t, y is a function of t. I need z to be a function of t also. What has to go here? Well, but what is y? Good, that's right. That's right, Hunu. Y is the sine of t. So that means z equals 2 minus the sine of t. And so these are my three parametric equations. Are there any questions on that? We'll go back to the solution for the example, but are there any questions? Okay. All right. Well, then if we go back here to the solution, the projection of that curve C onto the xy plane is the x squared plus y squared equals 1, z equals 0. I'm not going to, I want to just kind of keep things simple. I think you're comfortable with what you're seeing here. Okay, so there's x, and there's x, y, and z, x, y, and z. And so it follows then that the vector equation or position vector that's going to trace out this elliptical curve in space is r of t equals cosine of t I plus sine of t j plus 2 minus sine of t k. And t, it can be restricted from 0 to 2 pi. That equation is called the parameterization, or that vector equation is the parameterization of the curve C. Okay, it's no different than when you had parametric equations with two-dimensional things like circles and parabolas and stuff like that. Now, they also mentioned that in figure 6, the arrows indicate the direction in which C is traced out as the parameter increases. Okay, so if we go, T is your parameter. So as T increases, you're tracing out that curve in space. Okay. So that's an example. That's an example. A good example, actually. Okay, are there any questions? Okay, let's do an example here. Hold on here. I don't want that yet. One moment. something here. Okay, let's take a look at this example. Let me give you a moment to copy it down. Okay, so we have here a curve, a space curve. Okay, we have a space curve. And we wonder, hold on, I gotta have this, one moment here. This is my space curve. And we want to know at what points the space curve intersects the paraboloid. So for this problem, I'm going to say it's the right way. What component's missing from this space curve? The y component. Well, we have the parametric equations already. X equals t, z equals 2t minus t squared. And what's y equal to? What's 0? So yeah, we can put a 0 here. So this space curve lives in what plane? This space curve actually lives in a plane. It lives in the xz plane. So now let's talk about this paraboloid. This paraboloid. Is this a paraboloid that is, I mean, what axis is going through the center of this paraboloid? The x, y, or z axis? Z axis, that's right. And is this paraboloid opening upward or downward? Good, it's opening upward, okay? And it has to, because x squared plus y squared on the right is always positive. So that means the z coordinate is always positive. So it has to be opening upward. You know, it's opening upward, this paraboloid. And it starts from the origin, right? Well, so the space curve will pass through the paraboloid. How many points do you think it will pass through? on the paraboloid. I mean, it says at what points does the curve, that space curve, intersect the paraboloid? How many points do you think it'll intersect in? 2 sounds good to me. Good, good. So let's look at the solution here. Let's look at the solution. Well, let me ask you this. In order to find the points, what variable do we need to solve for? What variable do we need to solve for here? Well, we know why. Well, right, y equals 0. I mean, well, the curve moves through space because what variable changes? What variable is changing with time? Good, t. So if this curve intersects, if this space curve intersects the paraboloid, it will do it for, and it does it in 2 points, it's going to have to do it for 2 different values of t. So, all right, let's keep that in mind. What we want to do then is we need to find t. We need to find t. Okay, such that, well, I mean, when the space curve intersects the paraboloid at those moments, the space curve is touching the paraboloid, and so at that moment, z has to equal x squared plus y squared. Well, now for the space curve, the z component is 2t minus t squared, right? That's the z component. And the x and y components are t and 0. So this must be true. Well, based on that, we can then say 2t minus t squared equals t squared, and I can solve for t. Okay, are there any questions up to here? Let me give you a moment to catch up here. All right. Let me ask you this. When I had 2t squared equals 2t, 2t squared equals 2t, I remember when I had taught sort of like lower, more introductory algebra courses, some students would do this. They would divide by t, and then they'd say, okay, 2t equals 2, so t equals 1. But is this okay to do? No, you can't divide by the variable. Unless the variable is not equal to 0. And that's right, Mario. You need t is equal to 0. So, if we knew t were not equal to 0, we could divide by the variable and we'd be okay. But in fact, but you never know that ahead of time, right? So you can't divide by the variable. Okay, good. That's right. Oh, wow. Well, you learned something very good there. You learned something very good. So what we have to do is we have to solve this algebraically, and what we'll do is we'll bring 2t over to the left side. Now we can divide by 2, which is what we did to get, we divide through this equation by 2 to get the equation t squared minus t equals 0. And then, of course, we can factor out a t. So t times t minus 1 equals 0. And because of that, t equals 1 and t equals 0. And so those are the two times at which the space curve passes through the paraboloid. And so for those two times, then the points of intersection, and that's what is asked, right? We are asked at what points does the space curve intersect the paraboloid. For those times when t equals 0, the coordinate is 0, 0, 0. And when t equals 1, the coordinate's 1, 0, 1. And how do we get 1, 0, 1? Well, hold on, let me use my stylus. From r of t. That's right. So like, for instance, r of 1, let me do this differently here. How do we get 1, 0, 1? Well, all right. R of 1 is just equal to 1, comma, 0, comma, 2 times 1 minus 1 squared. Close it. That gets us 1, 0, 1. Okay, so this is really, section 10.1 is really an introduction to space curves. Okay, and are there any questions on that? Any questions on that? On that example? So that, you know, it's kind of important. You know, if this, for instance, were, say you had some, say you were targeting a surface that looked like a paraboloid, okay, and you wanted to know what are the points of intersection of your, say, missile and the paraboloid. Well, points of intersection, here's how you would get them, right? So they're important, right? We want to know these kind of things. A lot of applications. Okay, are there any questions before I stop the recording? Okay, I'll stop the recording.